Welcome to the Daily AI Update for June 23, 2026. We've got 8 stories today that are genuinely reshaping how AI works in the real world. We're talking about enterprise learning systems that actually retain institutional knowledge, agentic loops, agents running agents in the background without a ceiling, the science of fluid versus crystallized intelligence, and why one matters way more in an AI-saturated world. Then we have the first AI lawyer winning an actual English court case, OpenAI's massive cybersecurity play with something called Daybreak, Sakana's Fugu system breaking vendor lock-in through orchestration, self-improving agent harnesses that rewrite their own rules, and Claude Fable 5, a model so capable that the bottleneck isn't what it can do anymore, it's what humans can imagine assigning to it. That's a lot of ground.
That's a really full slate, and honestly, what strikes me is that these aren't disparate stories. They're all pointing in the same direction. Every single one is about moving AI from this experimental, chat with the chatbot phase into something foundational, infrastructure, real systems, real work.
Exactly. And what ties them together is a shift in thinking. Instead of asking what can the model do, which we've pretty much answered by now, the questions have become, how do we organize work so AI can actually do it at scale? How do we keep it from forgetting? How do we make it resilient? How do we prevent vendor lock-in? These are infrastructure questions.
And some of these stories directly create competitive advantage through structure, not just raw capability. Like, OpenAI didn't just release a better cybersecurity model, they built an entire ecosystem around actually fixing vulnerabilities, not drowning open source maintainers in reports. Sakana's routing across models so you're not stuck with one vendor. Agents learning from their own failures instead of requiring constant human handholding. These are architectural moves.
Yep, let's dig into all 8. We'll start with the Fable 5 story, because understanding how the economics and psychology of that model work is actually the frame for everything else. Then we'll move through the cybersecurity ecosystem, orchestration, the foundational systems work, and finish with the legal milestone. Strap in.
So, Fable 5. This is the story that honestly reframes what capability means at the frontier. The model costs $50 per million output tokens, which is, let's be honest, wildly expensive for daily work. But here's the thing, the model is so capable that you're not actually hitting a capability ceiling anymore. You're hitting an imagination ceiling. The constraint has flipped entirely.
Okay, so at that price point, you're not using this for quick summarizations or email drafts. What kinds of work actually justify $50 per million tokens?
Right, you're looking at 2-week problems. Gnarly, unassigned work. The stuff that makes entire teams sigh because it's too big or too ambiguous to fit into anyone's sprint board. Code refactoring across an entire legacy codebase, data cleanup projects, building comprehensive system documentation, analyzing months of trading data across multiple instruments. That's the scale where you're willing to trade tokens for time.
So you're not supervising constantly? You're not hovering over the model checking every step?
Exactly. That's the mental shift that's hardest to make. You spend 3 to 4 hours assembling a data pack, getting all the context together, defining the scope, marking what success looks like. Then you walk away. You treat the model like a senior stakeholder you've briefed, not a tool you hover over. The model expects human verification afterward, but during execution, you're hands off.
That's a pretty different relationship with AI than what we've seen people practicing for the last few years. Most people have been trained to ask small. You're saying that habit is actually the limiting factor now?
Completely. 3 years of working with smaller models trained everyone to think incrementally. Ask a question, get an answer, ask a follow-up. That's the interaction pattern that became muscle memory. But Fable 5 breaks that. The model is trustworthy enough to walk away from on truly ambitious tasks. The bottleneck now is whether you can even imagine what a 2-week problem in your own work looks like.
You mentioned post-work review is still essential, though. That's not an area where we're automating human judgment away.
Not at all. Visual taste, design quality, whether the solution actually fits your domain context, those still need human eyes. The model is trustworthy enough that you can walk away from the execution, but the output needs verification. You're not eliminating the thinking, you're repositioning it. Instead of thinking step by step through a 2-week problem, you're thinking about which problems are worth assigning and then reviewing the results.
So this creates a different job description, doesn't it? You're not a prompt engineer anymore. You're, what, a task architect? Someone who can see big problems and package them correctly?
Exactly. You need what the research calls task imagination, the ability to identify work that's genuinely valuable, gather the context that matters, define the constraints, and hand it off cleanly. You need to know your own domain well enough to say, here's something that would normally take 2 weeks, and I can't assign it to anyone else on my team. That skill is actually rare.
And I imagine for someone building a portfolio of AI-assisted businesses, launching fast across different domains, this completely changes the economics of what's possible. You could tackle problems that would normally require hiring or outsourcing.
Right. The constraint stops being, can the model handle this, and becomes, do I have enough context to hand this off cleanly, and am I willing to spend an afternoon assembling that context pack? For someone with 30 years in game development launching multiple ventures, you've got deep domain knowledge that can actually be packaged as context. That's exactly what Fable 5 wants.
Okay, so OpenAI just dropped a competitive move in the cybersecurity space. They released GPT 5.5 Cyber, and the headline numbers are 85.6% on CyberGym versus Anthropic's Mythos 5 at 83.8%. So technically, OpenAI wins the benchmark.
And that matters in a way, for certain kinds of comparative testing. But honestly, I read through this, and the benchmark numbers feel like the least interesting part of the story. The real move is something called Daybreak, and specifically, the Patch the Planet program. That's where the architecture thinking comes in.
Right? So break that down for me. What's actually happening with Patch the Planet?
They're pairing professional security researchers directly with open source maintainers to actually fix vulnerabilities, not just report them. And this addresses a real structural problem in open source. 94% of widely used open source projects have fewer than 10 developers maintaining them. So when AI starts flooding them with security reports, even accurate ones, most teams can't actually action them. The vulnerability report just sits there or gets deprioritized because there's no one to fix it.
So the problem isn't finding vulnerabilities anymore. It's remediation at scale. The maintainers are underwater.
Exactly. Codex Security, which is part of this ecosystem, has scanned 30 million commits across 30,000 code bases and flagged 70,000 findings. But they didn't just leave it there. They manually validated those and marked which ones are actually fixed. They're closing the loop that AI vulnerability discovery created.
But here's where it gets interesting politically. This model, GPT 5.5 Cyber, is not public. It's restricted to what they call trusted defenders, with monitoring and human review. You don't just get to spin this up yourself, and that ties directly into some pretty serious government concerns that just emerged.
Yeah, and this is where the week gets weird. Anthropic literally had to pull Claude 5 and Mythos 5 from their product lineup after the Trump administration raised concerns about public access to frontier cybersecurity capabilities. We're talking about a situation where a company actually had to remove their own models because the government essentially signaled that having them widely available was a national security problem.
And OpenAI's response to that is interesting. They're going restricted by design. Daybreak includes coordination with 8 governments: the US, UK, Australia, Canada, France, Germany, Japan, and South Korea. There's also partnership with major enterprises like Cisco, Cloudflare, CrowdStrike, Palo Alto Networks. This is positioning cybersecurity AI as critical infrastructure that needs to be monitored and coordinated at a government level.
The Five Eyes Intelligence Alliance actually released a warning about this. They said frontier AI could transform both offensive and defensive cyber capabilities in a matter of months, not years. So suddenly, you've got intelligence services paying very close attention to which models can do what and under what conditions they're available.
So the practical outcome is, the model is more permissive, it actively reduces false refusals when legitimate security researchers are doing authorized work, but you need to be vetted to access it, and that vetting involves government.
Right. Which actually makes sense from a harm perspective. Cybersecurity AI is different from general-purpose AI because the offensive and defensive applications are genuinely symmetrical. The same capability that helps you patch vulnerabilities can be weaponized, so restricting it to vetted defenders rather than going wide is a deliberate design choice.
Speaking of vendor lock-in, that Anthropic pull we just talked about is actually a perfect bridge to the next story. Sakana AI just launched something called Fugu, a multi-agent orchestration system that's specifically built to solve the problem we just described. What happens when your primary vendor gets restricted or pulls products? Fugu is their answer.
And this is elegant from an architecture perspective. Fugu is essentially a master general contractor sitting on top of a swappable pool of specialized models. You get a single API endpoint, OpenAI compatible, but underneath, Fugu is dynamically routing your queries across different models depending on what the task actually needs. It breaks the monolithic model dependency problem.
What's the performance story here? Because orchestration adds latency and complexity, so they need to prove this doesn't just feel good theoretically, it actually delivers results.
The numbers are strong. On Live Code Bench, Fugu scores 93.2 versus Fable 5's 89.8. On GPQAD, it matches Mythos Preview at 95.5. So you're getting frontier-level performance through orchestration rather than relying on any single monolithic model. 2 tiers, Standard Fugu for low-latency everyday tasks, and Fugu Ultra for complex, high-stakes workflows like cybersecurity analysis or AI research. Pricing is subscription, $20 per month for Standard, $100 for Pro, $200 for Max, or Enterprise pay-as-you-go at $5 per million input tokens and $30 per million output tokens for Ultra.
Okay, so from a resilience perspective, this directly addresses what we just saw with Anthropic. If Mythos 5 becomes unavailable or restricted, Fugu just shifts that routing logic to use a different model without your application breaking. But here's my question. If the routing is proprietary and you don't know which models are being used under the hood, how much transparency do you actually have into what's happening?
That's the trade-off built into the system. The routing logic is proprietary. Sakana doesn't disclose the exact models or coordination patterns because that's their competitive advantage. The system autonomously manages model selection and verification using learned strategies rather than hand-designed rules. You get resilience and performance, but you're trusting their orchestration layer. That said, they do let you opt out specific providers if you have compliance concerns, and you can disable prompt-based training data collection if that's a regulatory requirement.
Which brings us to the EU complication. I'm seeing that Fugu is currently restricted in the European Union pending GDPR alignment. What's the issue there?
The black box routing architecture is the problem. GDPR requires transparency about how data is processed and which systems it flows through. But Fugu's entire value proposition is that you don't need to know the orchestration details, you just get results through a single endpoint. That's a direct collision with EU data protection requirements. They're working through alignment, but right now, anyone in the EEA who wants to use Fugu is blocked. It's a good reminder that infrastructure choices have regulatory cascades.
So we've been talking about models getting more capable, orchestration systems getting smarter, but there's a foundational constraint that nobody's really solved yet. Organizations are constantly learning things their AI systems never actually get to use. A team catches a bug, figures out the root cause, corrects it in a ticket somewhere. Another team discovers a pattern across 100 workflows. Someone manually marks a false positive from the security system. All of that knowledge, corrections, root causes, escalation signals, just vanishes into silos. It never feeds back to the agents. So you end up with AI systems that don't actually improve based on what the organization has learned.
Right. And this is where people have been thinking about it wrong. The competitive advantage isn't going to be, we have the best model. By now, frontier capability is fairly commoditized. The real differentiator is whether your agents can learn from your organization's accumulated operational experience without constant retraining. So there's actually a whole architecture being proposed around this. 5 components, and they're worth understanding because they're not flashy, but they're foundational.
Okay, walk me through those 5 components.
Number 1 is memory, what actually happened, not the ticket, not the summary, the execution trace, the thing the agent did, the outcome, the feedback. Number 2 is knowledge bases, reusable guidance extracted from those traces, rules of thumb, patterns, things the organization has learned the hard way. Number 3 is data fabric, connected signals, security events, network behavior, observability data. Instead of agents operating in isolation, they can see signals across the organization. Number 4 is AI observability, tracking what the agent actually does. Not just did it complete the task, but how did it reason, what did it consider, what did it discard. Number 5 is a control plane, governed change management. So when you do feed something back to an agent, a new rule, a corrected pattern, there's verification and rollback capability built in. You're not just blindly updating agents in production.
Okay, but organizations have had documentation for decades. They've had playbooks, runbooks, tribal knowledge databases. How is this different from just having better documentation and telling your agents to read it?
That's the critical difference. Documentation is static. Someone writes it down, someone else reads it. Maybe. But this requires closing the loop automatically. Every workflow becomes a teachable moment. An agent runs, something happens, the system captures what occurred, extracts the learning, updates the knowledge base, and the next time a similar situation arrives, the agent benefits without human curation in between. It's not documentation that lives in a wiki somewhere, it's a feedback system, and the loop closes without waiting for someone to write a ticket or a memo.
That's a significant architectural difference. But here's what I'm curious about. The summary mentions cross-domain agent collaboration. Security plus network plus observability, creating richer operational pictures. Why does that matter more than any single domain's agent improving independently?
Because reality is cross-domain. A security event that looks like an isolated breach might actually be explainable by network behavior that the security team can't see. An observability anomaly that looks like a service degradation might be caused by a policy enforcement change that the network team implemented. If your agents operate in silos, each one has a partial picture and makes decisions based on incomplete information. But if memory and knowledge bases and data fabric all flow across domains, a security agent can say, wait, the network team discovered this pattern last week, and a network agent can say, this observability signal showed up in the security domain last month, and here's what it meant. You get a genuinely integrated operational picture instead of isolated incident response.
So the organizational learning becomes richer the more domains contribute to it. And presumably, this compounds over time. The more you feed back, the smarter the collective system gets?
Exactly. Which means the competitive advantage isn't, we deployed Fable 5. It's, We've built infrastructure so that every workflow, every correction, every pattern our organization discovers automatically improves our agents. That's not a model problem, that's an architecture problem. And it's durable. Even when frontier models change, your institutional knowledge stays with you. So we move from infrastructure thinking to execution strategy. There's a framework from Boris Cherny. He created Claude code about what he calls loops. And this is actually a pretty significant conceptual shift. We've gone from handwritten code to single agents that can do tasks. But loops are the next step. Agents continuously running other agents in the background, indefinitely, without you supervising.
So you're saying this is as big a change as moving from manual code to agents in the first place? That's a pretty strong claim. What makes loops that significant?
Because it fundamentally changes what you're trading. With a single agent, you're trading time for execution. You give it a task, it does the work, you get a result. You're paying tokens for throughput. But with loops, you're authorizing swarms of agents to work endlessly on problems like code refactoring, abstraction unification, continuous improvement, tasks that don't have a clean finish line. You're trading compute tokens for productivity gains that could be enormous. The key difference is you're not supervising the loop. You set it running, and it keeps improving until it decides to stop.
Okay, that stopping part is where I have questions. In traditional recursive programming, you have a fixed condition. When x equals y, stop. But you're saying this is non-deterministic? The AI decides when work is done?
Right. There's a popular pattern called the Ralph loop. The system summarizes the work it's done so far and asks itself, are we done yet? If the answer is no, it keeps iterating. If yes, it stops. But the decision logic is entirely up to the model. It's not a ceiling. It's a model deciding when it's satisfied with the output, which means you can't predict how many tokens you'll burn ahead of time, and you can't guarantee it won't drift or get stuck in a local optimum.
Which brings me directly to production concerns. If there's no token ceiling, no fixed stopping condition, and the model is making that call, what happens when the loop gets stuck, or when the token bill spins out of control? And what about drift? If the loop keeps refining something over 100 iterations, does it actually improve, or does it start wandering away from the original goal?
Those are the exact constraints you need to manage in production. You need oversight of token spend. You can't just set this running and walk away without monitoring. Drift is real. And classic AI failure modes, hallucination compounding, self-reinforced errors that spiral, those don't disappear just because you've got a loop. But here's the thing. For the right problems, the productivity gains justify the expense and the complexity. Code refactoring across 100,000 lines, data cleanup that would take a human team weeks, trading steady token burn for that kind of value prop is often the right call. You just need to go in with eyes open about what you're managing.
So it's not a general purpose tool. You're identifying specific, gnarly problems, high value, high effort tasks that loop well, and you deploy loops specifically on those. And that ties directly back to what we were saying about enterprise learning systems and continuous improvement, doesn't it?
Exactly. A loop running refactoring or optimization could feed results back into your knowledge base. Each iteration produces learnings. This pattern works better. This approach fails. This configuration is optimal. Instead of the loop just churning tokens, you're capturing what it discovers and embedding it back into institutional knowledge. So the loop becomes part of your learning infrastructure, not just a cost center burning compute.
So there's research coming out of Shanghai AI Lab that actually tackles one of the biggest bottlenecks in agent deployment, and it's not what most people are talking about. They've built a system called self-harness, where agents systematically debug and rewrite their own operating rules by analyzing their own execution traces. We're talking about system prompts, tools, runtime policies, verification rules, all the stuff that normally requires manual engineering whenever a new model drops or a domain shifts.
This is genuinely clever because it addresses what's probably the unglamorous part of agent work, the harness layer. Everyone focuses on model capability, but the framework, the rules, the constraints you wrap around a model often matter way more than the base capability itself. Self-harness runs through a three-stage loop. First is weakness mining. You analyze execution traces and categorize failure patterns. What types of mistakes is the agent actually making? Second is harness proposal. You generate minimal, targeted modifications to fix those specific weaknesses. You're not doing generic prompt inflation, you're doing surgical fixes. Third is validation through regression testing before you promote those changes to production. So you're not guessing whether a change helps, you're proving it.
Okay, and the performance numbers are actually significant. They tested this across 3 different models: Minimax M 2.5, Quen 3.5, and GLM5, and saw improvements ranging from 33 to 60% without any human intervention and without upgrading to stronger external models. So the system is genuinely discovering model-specific fixes, not just generic prompt engineering. But here's my question. Why is harness engineering even that important? Shouldn't a better base model just solve these problems?
That's exactly the misunderstanding that costs teams months of wasted effort. A better base model helps, sure, but the harness layer, the runtime policies, the tool constraints, the verification rules, that often determines whether an agent actually performs well in your specific domain. An agent might be brilliant at raw capability, but terrible at following your operational constraints. Or it might have blind spots in exactly the domain you're trying to solve. Manually tuning for those blind spots normally requires someone sitting down, running the agent, seeing it fail, debugging why, modifying the prompt or the tools, and testing again. That's weeks of iteration every time a new model drops, or every time you want to shift to a new problem domain. Self-harness automates that cycle. The agent discovers its own weaknesses, proposes targeted fixes, validates them, and you just approve the ones that work.
So this directly solves a scaling problem for someone launching multiple AI-assisted businesses. You don't want to spend weeks tuning harnesses for each new venture or each new model release. The system learns what works and what doesn't, and evolves automatically. That compounding efficiency is massive when you're running a portfolio approach.
Exactly. It's the same infrastructure thinking we keep coming back to. Self-harness takes what would normally be manual, repetitive debugging work, the stuff that slows down deployment and makes it systematic and automatic. And because it's discovering model-specific fixes, those learnings actually feed back into your institutional knowledge base. When the system finds that a particular loop breaker rule solves problems for Quen but not for Minimax, that becomes part of what the organization knows. You're building a library of harness patterns that travel with you across model changes. So we shift gears here to something that's less about capability benchmarks and more about understanding what kind of intelligence actually stays valuable when AI gets good at everything else. There's a distinction between 2 types of intelligence that most people conflate. Fluid intelligence is the ability to navigate novelty, adapt to unfamiliar contexts, and generate solutions without relying on memorized patterns. You've never seen this problem before. You don't have a template. You have to reason through it fresh. That's fluid intelligence. And then there's crystallized intelligence, accumulated knowledge, retrieval, the stuff you've learned and stored over time.
Okay, so crystallized intelligence is basically what we'd call expertise or domain knowledge. The playbook you've internalized.
Exactly. It's the patterns you've seen 100 times, the decision trees you've learned, the frameworks that work in your domain. And here's the thing. Modern AI systems are genuinely phenomenal at crystallized intelligence. They can retrieve knowledge, pattern match, apply learned frameworks. That's essentially what language models do at an enormous scale. They're optimized for crystallized recall. But genuine novelty? Truly unfamiliar contexts? That's where they start to struggle.
So when you say they struggle with novelty, you mean they're fine with problems that are variations on things they've seen in training, but genuinely new situations, situations that require reasoning without a template, that's harder for them?
Right. And that matters because fluid intelligence is what enables cross-domain transfer. It's what lets someone who knows music theory pick up game design and see connections nobody else sees. It's what lets a security researcher look at an observability anomaly and think, wait, this pattern reminds me of something from a completely different domain. Fluid intelligence is about making unexpected connections and adapting when the standard playbook doesn't apply. The human capacity for that stays valuable even as AI dominates crystallized retrieval.
Is this basically just saying AI is great at known problems but struggles with truly new ones? Because that feels like something we've been saying for a while now.
It is, but framing it as fluid versus crystallized intelligence changes what we should actually be training people for. For the last decade, we've been building careers around crystallized intelligence. Accumulate expertise, build domain knowledge, specialize, but that's becoming the thing that gets automated. The thing that doesn't get automated is the ability to walk into a situation nobody on your team has handled before, see the weird edge cases, connect it to domains you've touched in completely different contexts, and reason through a solution. That's fluid intelligence. And it's becoming more valuable, not less, as routine retrieval gets automated away.
So the implication for careers is that become an expert in your domain is actually increasingly bad advice? The better move is to cultivate the ability to rapidly learn new domains and handle weird situations?
Not bad advice exactly, but incomplete. You still need some crystallized knowledge. You can't reason about problems in a domain you've never touched at all. But the premium is shifting. The person who knows everything about their narrow specialty is competing with AI that knows the same thing. The person who can see across domains, handle anomalies, adapt when the standard approach fails, that becomes rare and valuable. And in a world where you're launching multiple ventures across different domains, launching fast, fluid intelligence is what actually lets you do that. You're constantly operating in novelty.
Okay, so there's a news milestone we should flag. An HR consultant has just won an English court case using an AI-powered legal service. This appears to be the first successful use of an AI lawyer in England's actual court system. Not a simulation, not a legal research tool, an AI system acting as counsel and winning.
Wait, so the AI actually presented arguments in court? Or was it more of a prep tool that the human lawyer used? Because that distinction matters a lot for what this actually proves.
It was AI-powered legal service providing counsel, and the case was won. The details aren't fully granular about whether the AI was in the courtroom directly or was the primary architect of the strategy, but the fundamental point is, an AI system handled legal representation in a real, binding court proceeding, and it succeeded. That's not a technology demo. That's an institutional system accepting AI as counsel.
Okay, so here's what that actually signals. Legal proceedings are high stakes, regulated, consequential environments. Failure carries real costs. The client loses their case. There's human judgment involved. There's precedent. There are rules of evidence and procedure. If an AI system can operate successfully there, it validates that agentic AI is genuinely ready for regulated domains where accuracy and reliability actually matter. This isn't like an AI writing marketing copy where pretty good is acceptable. This is where wrong means you lose.
Exactly. And what makes this different from, say, AI writing a legal memo is that it's operating within existing institutional frameworks. The court didn't have to build special rules for AI lawyers. The system worked within the normal processes. The case was adjudicated the same way any other case is. That's real integration, not a special case experiment.
So the implication extends beyond just law. If agentic AI can operate successfully in one of the most regulated, human-centered, high-consequence domains that exists, that's proof of concept for deployment in other regulated spaces, finance, healthcare, critical infrastructure. Not proof that those domains are next, but proof that the technology has matured past interesting prototype into can operate in real institutional contexts where being wrong has actual consequences.
So let's zoom out for a second. We started today talking about 8 stories, and if I'm being honest, that felt like a lot of ground. But looking back at everything we've covered, enterprise learning systems, agentic loops, Sakana's orchestration, self-harness, Fable 5, the AI lawyer, Daybreak, fluid intelligence, there's actually a single thread running through all of it. And it's not about models getting incrementally smarter, it's about infrastructure. The way we organize work, capture knowledge, route complexity, and prevent lock-in.
Right. And that's the shift nobody's really talking about yet, but everyone's feeling. For the last few years, the question has been, what can AI do now? We get a new model, we benchmark it, we see what it can handle, but somewhere around now, maybe June 23, 2026 is the inflection. The question became, how do we organize our work so AI can actually do it at scale without falling apart? Those are completely different questions.
Exactly. Look at what we actually talked about. Fable 5 doesn't win because it's marginally smarter. It wins because the economics change when you can hand off 2-week problems and walk away. Enterprise learning systems don't win because documentation is better. They win because the feedback loop closes automatically, so every workflow teaches the system without human curation. Sakana's Fugu doesn't win on benchmarks. It wins because you're not locked into a single vendor anymore. Self-harness doesn't require stronger models. It requires the organization to systematically debug and improve the runtime layer. Even the AI lawyer winning in court isn't about legal reasoning. It's about operating successfully inside an existing institutional framework.
It's infrastructure thinking. And that's actually good news, because infrastructure is durable. Models will change. New vendors will emerge. Benchmarks will shift. But if you've built your work around learning systems, if your agents can self-improve, if you've got orchestration that abstracts away vendor lock-in, if your knowledge feeds back across domains, that survives the next model wave. It survives regulatory changes. It survives geopolitical restrictions, like what we just saw with Anthropic. You're not chasing capability anymore. You're building resilience.
And I think the real insight for listeners is this. Whether you're launching AI-assisted businesses, building products at scale, running critical infrastructure, or just trying to keep your team from drowning in toil, the limiting factor right now isn't model capability. We've basically solved that. The limiting factor is whether you can structure your work so AI can actually be useful at the scale and complexity you need. Can you imagine big enough problems? Can you capture what you learn? Can you prevent being locked into one vendor? Can you make your agents self-improving? Those are the infrastructure questions that actually matter.
So as we wrap, we'd love for you to think about which of these trends actually touches your own work. Are you someone who could benefit from enterprise learning systems? Do you have gnarly problems where agentic loops could drive real value? Is vendor lock-in a risk you're carrying? Is your harness layer the bottleneck instead of the model? These aren't hypothetical anymore. They're infrastructure decisions you're probably facing right now. And the organizations that get this right, the ones thinking about infrastructure instead of chasing capability, those are going to pull ahead. We'll be back tomorrow with more updates. Thanks for listening.